Anyway, it's my pleasure to be here in Barcelona. It's my first trip here, and I'm pleased that you brought snow for me so I'd feel at home being a Canadian this morning. So it's funny, 2 days ago I was out on the beach and there were people laying in the sun, and today there's snow. So it's a changing world. But anyway, I'm here representing ACI. I'm not going to talk. I'm just going to give a few slides because it's my obligation since they helped bring me here to talk about the ACI through this ambassador program. And they have this vision where they want people to have a better understanding of concrete and disseminate that knowledge. ACI is a fairly large organization. They've taken a number of initiatives, and if you turn your head, you can sort of read these initiatives, some of these things recently. They've been pushing things like webinars. They do certification programs. They've certified over 400,000 people and workers for quality construction, finishers and testing agencies. They run a university program which is done through webinars and seminars. They have 2 conventions a year. Our convention's in Salt Lake City next week. So I'll go home from here and then right to Salt Lake. So and they have a research foundation on the right-hand side that distributes money. They've increased the research money that they're distributing, and people can apply once a year for funding for that. There's over 20,000 members of this, and from 129 countries, and they've just opened an office in the Middle East, so they're going to have a physical presence in the Middle East. Our current president is from Lebanon, and so it's a fairly large organization, fairly international. Although it's North American-centric, it certainly has that. And I've been a member for a long time. I can tell by my gray hair. But and I'm on the board of directors currently, and I'm just coming on as the chairman of the Durability Committee and developing a new initiative on durability specifications. So it's been a rewarding experience being part of ACI. So that's my ACI spiel. But now this is what I want to talk about. And I guess it didn't make the program. I thought I'd sent the abstract in, but this is sulfate resistance, and it's related to recent developments with Interground limestone in cements that's not new in Europe, but it's relatively new in North America. And we were concerned about things in terms of potential for Thaumasite sulfate attack, and we instituted a test method in the Canadian standards, which we then have now removed, which is we maybe overthought the problem a bit. So this is presented with my PhD student Reza Hahani and Michael Thomas at the University of New Brunswick and his former PhD student. And again, people are aware of the Thaumasite issue, potential for pretty extreme damage because it attacks the calcium silicate matrix of concrete. Although this concrete didn't contain limestone cement, it formed probably due to the CO2 in the groundwater. We have a severe sulfate issue in western North America. I just shows the little box in Canada, western Canada, and we have very high sulfates in ancient seabed. We get high concentrations, higher than you would find in most places in Europe. People think that we have these crazy high sulfate content test methods where we put our samples in up to 33,000 parts per million sulfate ions. But in the States, just below that map, they have concentrations that actually get that high in the field. So we have very high concentrations in Western Canada that we have to deal with. And as a result, we have our specifications for sulfate attack are very similar in Canada and the US. And we have basically, it's a simplified program, less complex than the EN standards for sulfates. We just simply have 3 categories of different severities. And when we decrease the water-cement ratio as it gets more severe. We have requirements for cement, moderate sulfate-resistant or high sulfate-resistant cements, and we can qualify mixtures of blended cements or mixtures of SCMs, supplementary cementitious materials, and Portland cement by using a mortar bar expansion test. And so we have this option. And so that's been working for us and pretty much has solved problems, except when we introduced limestone about 10 years ago into the Canadian standard with up to 15% underground cement. So it's similar to a CEM 2A SEM2AL in the EN standards. And there were a lot of reasons for doing that, and of course the industry and cement industry in North America is largely European owned. You've got Holcim Lafarge, you've got Heidelberg Cement, and so they're had interest in bringing this technology into North America, and they used Canada as their first stop. It's now moved into the United States through the ASTM more recently. But we adopted this first, and we designed these cements to have the same strength development, setting time and strength development properties as regular Portland cement. Well, when this came in, there was concerns amongst the members of the committee about various things, and we looked at sulfate attack as one potential area where there hadn't been a lot of research done on the effect of limestone cements in sulfate environments, and especially because of the concern at the time with Thaumasite sulfate attack, which involves carbonates and low temperatures and sulfate ions. And so we wanted to make sure that we did some research before we allowed these cements in sulfate exposures. And we know that it's when it does happen, it's pretty severe. It's very rare, but when it does happen, that used to be concrete up on the right, it destroys the calcium silicate matrix. So we wanted to make sure we weren't introducing something in the standard that could cause us a problem in these severe environments in a fairly cold climate. And so our normal test method, which is the ASTM C1012 test, I know it's been criticized for maybe not representing all things, and I know Esperanza's been involved with the Rilem committee on developing a better test method for the European experience or world experience. But we've had this test method since around 1981. You cast mortar bars, you wait till they get to 20 megapascal strength, you put them in a pretty strong sulfate solution, and you immerse them and measure the expansion. But at room temperature, you're not going to pick up Thaumasite. It will form etronite typically and cause that swelling. But so with Thaumasite, we're thinking, well, what do we do about this? So we developed another mortar bar test at cold temperature. We put them at 5 degrees. Basically the same test method, but storing them at a lower temperature. And so we adopted this as a way of moving forward to allow the use of limestone cements with supplementary cementitious materials or blended systems in the sulfate environment. And this was in 2010, so 2 years later, we came up based on mortar bar testing. And that's the test method. It's exactly the same test method except for the temperature. And of course, one of the problems with that is that at 20 megapascals, which you typically get within 1 or 2 days, a lot of things like fly ashes haven't done anything. They haven't done any pozzolanic thing in 2 days. Then you put them at 5 degrees C and put them to sleep. And so the problem with that is that it then made the pozzolans look very poor in the system. With slag, it wasn't so bad because slag tends to react more quickly, and silica fume as well. And then so the low temperature doesn't hurt it, but certainly fly ashes were impacted adversely by this cold temperature. And this just shows some of our early experiments with different amounts of slag. This is a high C3A. So this is a typical high C3A Portland cement, and this is the same cement replaced by slag, and then different amounts of interground limestone in the system. Now we only allow 15%, but we did one deliberately at 22%, and you can see the damage. And some of this has to do with Thaumasite, although as we found later, it happens after the fact. And if you put slag in, you don't have any problem after 18 months. And we did X-ray diffraction, amongst other things, and what we found was at 23 degrees, these are the 23 degrees with different amounts of limestone, we see etronite, gypsum, portlandite, but at the low temperature we also see the doublets related to Thaumasite and etronite. So the Thaumasite does form at the low temperature in the debris, not so much in the intact bar, but in the debris that forms in the bottom after the fact. And as we found later, the etronite forms first, the failure occurs by etronite, and then with prolonged exposure of the pieces, the small bits of debris, Thaumasite forms as a secondary reaction. And again, this is the sort of expansion we would see if you have sufficient replacement with slag. Our expansion limits up there, the red line here, but our expansions, regardless of limestone content, are essentially the same. And when we have 50% slag in there and they're totally mitigated, again, it doesn't matter how much limestone, and we're not seeing any evidence of Thaumasite formation. But as I said, this test method we put in 2010 caused all kinds of problems in the industry when they started using it, because many of in the western areas where the high sulfates are, they don't have slag, they have fly ash. And of course, the test method didn't show that to work very well. So we said, well, are we really simulating concrete performance? So we started doing concrete testing. So in 2010, we embarked on a couple of concrete programs, fairly large programs. I did it in Toronto, and Michael Thomas did that at the University of New Brunswick. We did different mixtures, but at Toronto I did 53 different types of concrete of different water binder ratios, different cement types, and different supplementary cementitious materials. We looked at, and we did visual inspections, mineralogical analysis, microstructural analysis, and length change, along with other tests. And we did some in the laboratory at 5 degrees Celsius, where we stored concrete prisms in containers in various solutions of either mag sulfate, sodium sulfate, or calcium hydroxide as a baseline, and we used different concentrations depending on the water binder ratio. And we also did a field site. We don't have sulfate soils in Toronto, so we decided to create an underground site in tanks that would allow us to simulate the temperatures that occur in foundations, where we might have cool temperature attack. And again, so we did the various concentrations, and the one we picked was 15,000 milligrams per liter, or 15 grams per liter of sulfate, which represents the condition in Western Canada, sort of the worst case condition. And we would require 0.4 water binder ratio for those situations. Some of my slaves, some people call them graduate students, but I call them slaves. And we've got over 1,000 concrete beams that we filled in there. We put them in sulfate. They're covered in insulation. We come back next year, and every year we take them out. They're now over 7 years old now. So I need slaves every summer to come out and put those things in. And we did some work a little bit after. This is some cements, and what they have. The top here, we have a high C3A cement. We have the same clinker with 9% underground limestone, one with 15% underground limestone. And this is the surface damage after 1.5 years in the field site, where it varies between about 3 degrees and 15 degrees Celsius during the year. And we see, regardless of the limestone, even if there's no limestone in the cement, we're seeing exactly the same thing. We see some evidence of Thaumasite and etronite, but there's no difference with the limestone content. So it wasn't influencing the result. And now, last summer, based on last time the slaves were busy, we found that after 6.5 years, it didn't matter. The limestone did not impact on the result. Even the sulfate-resistant binders, the low C3A Portland cements, and blended cements that are sold commercially for sulfate-resistant environments, they showed minor surface damage. And the ones with, regardless of limestone, if they had sufficient supplementary cementitious materials, did not show damage, as I've shown in green here. And my student developed a color coding system just to make it easier, because they're very small photographs here. And so green means there's no damage, red means that they're severely damaged, and the color scale goes on like that. So it's just a color scale, because I've just got some composite photos here. So the top left here is a straight high C3A Portland cement with 40% slag after 5.5 years. There's some minor damage here, just small corner damage. And that's true whether it's limestone or not. There's no difference due to the limestone. If we put enough slag in, 50% slag, which we would normally use with that particular clinker, it is no damage at all. This is a sulfate-resistant cement that's currently allowed in the system. So a low C3A Portland cement that have been used for almost 100 years in Western Canada, and they're severely damaged in this environment. So after 5.5 years, they're severely damaged, but the mixture of even a high C3A cement with sufficient slag is fine. And this is another system with 30% fly ash with a moderate C3A clinker that's also sold in Western Canada for sulfate environments. So we're seeing there's no difference. That's a high sulfate-resistant Portland cement after 5.5 years to see just a more close-up of the damage that occurs. There's a different Portland limestone cement with about 11%, 10.5% limestone, again with 40% slag or 50% slag. Two different sulfate-resistant Portland cements. We decided to expand the program in 2012. And again, there's no difference with the limestone sufficiently mitigated. They're no worse, if in fact better than what they're doing now. And this is just in different solutions. So the top bar is sodium sulfate, the magnesium sulfate, sodium, magnesium of different systems. So again, the limestone's not having any impact in terms of they're in better shape than what people are doing now in the industry. And we did some microstructural work. I'm not going to show all that because of time. We've done X-ray diffraction, SCM work, and we found no evidence of Thaumasite sulfate attack inside the concrete. These are just some thin sections that we then did X-ray microfluorescence on just to look at the sulfate penetration from the surface, and then we also put these into the electron microscope later on. And whether it had limestone or this straight Portland cement with or without slag, there's a 15% limestone with or without slag, and then a sulfate-resistant Portland cement. It didn't have much impact on the rate of penetration, and we never saw any Thaumasite inside the sample. The only time we saw Thaumasite was when pieces fell off the surface, and they then further deteriorated in the structure. Okay. So not wishing to go too far, I just want to conclude by this, that the concrete exposed to sulfates at either cold temperatures or mixed temperatures where they're going up into cycling temperatures between 3 and 15 degrees Celsius showed that if you have sufficient mitigation with supplementary materials or using blended cements, that we got equivalent or superior performance to sulfate-resistant systems that are currently used, and that the mortar bar test that we'd originally developed wasn't very reliable in predicting the concrete performance. And then we found that the traditional mortar bar test we did, the ASTM C1012 test, at room temperature was sufficient for telling us whether a system is mitigated or not. Because if you mitigate it for etronite, you also mitigate it for Thaumasite, is our finding of that. So the test was too aggressive, so last year we removed the test method from our standards that had been there since 2010, and we've now removed all the restrictions on the use of limestone cements in sulfate exposures. And ASTM has copied that as well. They didn't adopt any of these measures. They waited to see what we were doing in Canada. We were the test bed for the Americans. And so we published some of this report. Mike Thomas and I published this, and you can download it for free from the web, from the Portland Cement Association, who, of course, were interested in our research. And this is the recommendations we found. And it contains a lot of the data we developed for this program. So it was a long program, but like I said, it's probably the most research ever done on sulfate resistance in North America to approve a cement system. But it was a very interesting experience. Anyway, thank you very much. Appreciate the opportunity.
Thank you very much, Doug. Maybe don't go too far because maybe we have time for one question. Quiet. No questions? So this... Oh, Mark, you have a question.
Doug, I understand why you use the test method, but you didn't quite explain why you were doing prescriptive requirements. Can you replace them with some performance requirements?
We had some prescriptive requirements. When we first did this, the people in the Western Canada in the ready-mix industry were very nervous about allowing this type of cement in exposures where they knew they had severe sulfate problems. And if they don't address sulfate resistance there, the concrete doesn't last 5 years. And so they were nervous about bringing a new cement system in. And so we said, look, let's sort of a suspenders and belt and suspenders approach. We put in a test, which we thought was a performance test. We put in prescriptive limits so nobody could get around it, saying you have to use sufficient amount of fly ash or slag to mitigate the problem as well. But then we found out that the regular test method would give us that same performance. So we didn't see the need to have that additional prescriptive requirement in the system. It's sort of self-regulating. If you have the data to show that it doesn't expand in the mortar bar test, then you have sufficient mitigation. But it was just a nervousness issue. And I think that we've because of this research program, we've calmed down the industry, and I feel more comfortable with it.
All right. Thank you very much once again, Doug. So